Okay, so batteries may seem like they're super boring and complicated, but they, like everything else in chemistry, is just simple oxidation reduction reactions. And there's actually some fun, interesting things about it. For example, one of the very first Voltaic cells, which, in case you didn't already know, the Voltaic cell is the thing that looks like this, where you have the one glass and you have your salt bridge, and then you have the other glass and you have electricity transferring from the anode to the cathode using a wire. And the first Voltaic cell was created using a dead frog, where they took a frog leg, like so, and stuck a thing in this end and a thing in this end, and they connected it with a wire, and the frog leg was like because they put electricity through it. And so the frog leg has nerve endings here, and they still work even if the frog is dead. But essentially the frog leg was the salt bridge, which I think is pretty interesting. You know, you wouldn't think that the most interesting part of chemistry came from a guy playing with a dead frog, but there you go. So let's say that you have a light bulb, and you're like, man, I really want to light this light bulb up. And your mom is on a diet where she only drinks zinc water and copper water. And these are ions. And and I get that it can be hard to tell what's supposed to be dissolved in water and what's not supposed to be dissolved in water, but a good way to remember that is that water is polar. It is polar. And if you want to dissolve something in it, it has to have a charge on it, or it has to also be polar. So the zinc, the waterborne zinc is polar, because it dissolves in water. And if it wasn't polar, then it would just be resting at the bottom like sand. So you have this light bulb because you are bored and you want to knit, and it's the middle of the night and you can't because all of the light bulbs in your house are broken, or you just use candles. But everyone will know if you light a candle, so you have to use a light bulb. So you take your zinc water and you put it underneath one side of this wire, and then you take your copper water, and you put it underneath the other side, and it's like, okay, that's cool. Now you have two waters connected by this wire, and then you have a light bulb here. Like, that's great. Excellent. You need one other thing. You need some metals. So the metal is the non-polarized version of the metal. The solid metal in your galvanized cell. So here, this is just regular old copper. It's just Cu in a big clump with a bunch of other Cus in it. They're all chilling, they're having a good old time. And here on this side is zinc, and it's just a bunch of zincs in a clump with other zincs. And this is the most common example because these are like the two least expensive metals that you can find that have a big enough difference in electromagnetic energy that you can actually use them and demonstrate them in like a classroom setting. So if you did an experiment with these two, I wouldn't be surprised, because, you know, there's other metals that are better for it, but you don't want to create like a lithium gold battery for obvious reasons, and those obvious reasons is that, like, it would be really expensive. Okay, so zinc is a less electromagnetic metal than copper is. And for that reason, because these metals are connected to each other through this wire, they can travel, electrons can travel across the wire into this copper cell. So what's happening over here is, if we blew this up, you would see that there's a bunch of zinc ions. Actually, they're not ions, they're just regular old zinc atoms. And there's a bunch of zinc ions in the water. They're just sort of free-flowing in the water. The thing about zinc is that it's kind of chill. It's like chill. It doesn't really get angry or stressed out if it becomes an ion. And so the copper over here is losing its freaking mind that it's in the water and that it's an ion. It's like, I am just so distressed over the fact that I am in the water and I am an ion, and so it electrochemically sends a message to the zinc over here that the electrons are aware that this copper is losing its mind over the fact that it's in the water and that it's an ion. And so the electrons are like, okay, zinc, we're leaving you behind and we're going across the wire here to the copper, and that process is like this. So this is the bar of metal, and so the electrons leave this zinc, and this zinc then pops off and just floats in the water. And the zinc is stabilized by the fact that there's water molecules all over here, and the negatively charged O, the partially negative O, stabilizes that 2+ on the zinc. In the copper, you have the metal bar with the copper atoms that are not ions, and they're trying to chillin' in here. They're the most calm copper atoms. But these copper atoms out here that are positively charged by 2 are really upset. They're so upset that they're 2 charged, and then you have these electrons that come through here, through the wire down to the copper, and they're like, hey, chill out, dude, like, it's okay, we'll help you, you know, we'll add ourselves to you, and then you can stick onto this bar now. And so the copper atoms in this solution slowly get added to this bar as the solution of this one decreases. So the solution of copper ions on the copper side of the battery, on the cathode, decreases. Now, okay, so let's say you built this for some reason because you wanted to light your battery, light your light bulb. It would run for like -2 seconds. Like, it would not last for very long. And the reason for that is because eventually the zinc would start getting fed up by the fact that there's so many 2+, and the copper would start getting nervous because all of the copper ions are gone out of the water and now they're all in the bar. And so that leads to a salt bridge. And so a salt bridge, and in case you didn't know what salts are, it's an ionic compound where you have two ions in a really close connection with each other, and they're very stable. And so usually you have like a piece of paper or something soaked in like a salty water. And so let's say for this case we have SO4Na. So this would obviously, Na2, this would obviously break up into 2 Na plus and SO4 2 minus. And so here you have this negative ion can go over here and chill these dudes out. So the net charge is neutral. So because for every zinc ion that becomes positive, you have one SO4 2 minus that comes over and neutralizes the whole vial with zinc water. And then over here you have 2 Na plus, and that comes over and neutralizes the net change. So for every copper cation that becomes an anion, the sodium comes to neutralize the effect of the whole vial. So that's the purpose of a salt bridge, is to keep everything neutral. Otherwise, it would be really ridiculously slow, and it would just not happen at all. Okay, and then also, there's some contingency with the fact that, like, hey, these are in two separate things. Why don't we just have them in, like, one thing with both of the copper and the zinc, and then both of them? But that would be really fast. It would happen instantly, and it would happen really quickly, and it would be really hot. It would probably actually explode. So that would be bad. You can't have that. Okay, anyway, I hope this was helpful. If it wasn't, then you can let me know and I'll try and come up with a better explanation. There's not really a good way to use an analogy on this one. But I can try and think of one if you need me to. Okay,